Hello, good day to all. Dr. Kankaria, thank you so much to you and your family and institution for this very kind invitation. I am delighted to present this lecture to you, and especially considering that Professor Pallikaris is in the audience. It is very appropriate. I have been very fortunate to witness two paradigm shifts in laser vision correction. And the first was thanks to your guest of honor, where we all moved from doing our primary laser vision correction as PRK to doing LASIK. This was an absolute paradigm shift in laser vision correction. When we went from surface ablation to doing an internal stromal ablation that later developed into corneal optical engineering. We then witnessed an era of refinement. We had better lasers with flying spots and trackers. We got better diagnostics with wavefronts and topographies and tomographies and epithelial maps. And then better nomograms, personal nomograms or industry-wide nomograms that helped us refine our outcomes. And we were getting better outcomes. 90% of patients were getting 20/20 or better, and less of an increase in dysphotopsia than previous with our earlier versions of laser. And then we struck a plateau that has been there for the last 15 years until now. This is the second paradigm shift, ray tracing LASIK, where it goes from population optimization to individual optical simulation and planning, and then delivery to the cornea. This was a very necessary simplification initially, where we have a complex optical system, and this was dissolved into or compressed into sphere, cylinder, axis. Of course, we're going to lose some of the information in translation. And when we started doing personalization, instead of using just the manifest refraction, we started adding single diagnostic personalizations. So either based on the eye's wavefront, the ocular wavefront, or based on corneal topography or tomography, topography-guided treatment, to now becoming fully personalized treatments based on an integration of wavefront, corneal tomography, biometry, anterior chamber diometry, and then ocular modeling and wavefront analysis. And this gave us the ability to develop a digital twin. And besides just having this digital eye model or avatar of the patient's eye, the treatments could now be simulated on this eye and refined through an iterative process to get the very best outcome for that eye. So individualized optimization. The ray tracing guided LASIK is designed to provide maximum personalization with simplified decision making and planning with the most exquisite patient outcomes as a result. The 3D eye model allows the ablation profile to be created on the digital twin using all the aspects on the eye in the decision-making process rather than just one ocular characteristic as with prior customized procedures. So is this all theory or has this been proven? The original ray tracing guided LASIK study was performed in 2009 and published a couple of years after. There were 3 different devices: the wavefront analyzer, a lens star biometer, and the wavelight oculizer. And a ray tracing algorithm was generated using these multiple devices and installed on separate computer. There were 3 study sites, and the patients were higher myopes with more astigmatism, as this was the group that was deemed to show the most value from this technology. The European study, which was done more recently, was done within a device with one device. So one device capturing all the information sufficient to generate the eye model. It was done in 4 centers in Greece, Germany, and Australia. And in both instances, the initial study done in the Wellington Eye Clinic and with Theo Seiler and Matthias Maus, the best studies we'd ever seen in that specific cohort of patients, to the European-wide study, which again showed the best results seen to date. The post-market study in Australia, Germany, and Greece in 2020 to 2021 included 224 eyes with 3 months follow-up. These 2 studies, the Phase 4 study and the real-world study, demonstrate that ray tracing guided LASIK was equally effective at correcting myopia and myopic astigmatism. Half the eyes achieved uncorrected distance visual acuity of 20/12.5 and 8% achieved 20/10. There was a statistically significant decrease in spherical aberration. This decrease in spherical aberration is shown here and was across the board, even for high myopes in the -5 and -6 level. The beauty of this technology, however, is that these outcomes are replicated everywhere. In our own clinic, in more than 250 eyes, we are seeing exactly the same outcomes. In various US-based centers, in other European centers, and other global centers, including India and China. Exquisite refractive outcomes, visual acuity outcomes, and reduction in spherical aberration. This time around, all 3 devices are incorporated into one device called the sitemap. This includes optical biometry, corneal tomography, and ocular wavefront, and this device has everything it takes to develop the 3D avatar eye model. The eye model generated by the sitemap includes personal details like biomechanics and corneal wound healing that are expected to refine the outcome. The wavefront examination is achieved with a Hartmann-Shack aberrometer. Optical biometry is acquired, and corneal anterior and posterior data is provided by the Scheimpflug scan. All 3 scans can be seen on one screen on the sitemap, and this is all the information required to create the digital eye model. The ray tracing algorithm has 4 steps. Step 1 is creation of the 3D eye model based on the sitemap device data. The lens is then reconstructed, ensuring that the wavefront still applies to the reconstructed lens. The iterative process starts whereby the 2000 light beams directed through the virtual eye are followed to the macula. If all are converged, the ablation profile is ready. If they do not all converge on the fovea, then ray tracing is applied to help make the changes to the cornea so that all the rays converge on the fovea. This process is iterated until perfect and can happen hundreds of times. The duration of this entire process never exceeds a minute. Epithelial remodeling and expected biomechanical responses are also part of the algorithm, and hence the results tend to improve with time despite being excellent on day 1 post-operative. We have found that we are getting our best results when using cycloplegic data. It provides a stable baseline. Accommodation has the ability to alter optical inputs. The truth is that the diagnostic sitemap has all the information to create the model. The iterative ablation profile testing is occurring on the laser. As a result, we see, besides the spectacular outcomes, we see a narrower outcome spread. There are far fewer surprises on either side of the bell curve and better performance in demanding eyes. I see ray tracing guided LASIK or Wavelight Plus as continuity, not disruption. It's the same invention. It's now just been driven and informed by simulation through optical modeling and this iterative process, and it's defined a new era in laser vision correction. Thank you again for your very kind invitation. Thank you for your kind attention. Thank you for the privilege of being able to celebrate with you in this remarkable milestone of 40 years of refractive excellence, and for allowing me to share this amazing achievement with the founder of LASIK, Professor Pallikaris. Thank you all and have a great meeting.